Hi, good morning. Dave Anderson will continue his introduction to Equivariant K-theory.
Good. So thanks for coming back. So I'm going to not exactly continue where I left off, but jump into maybe the main the features of equivariant K-theory this time. So as you know or learned or are about to learn, one of the main advantages of T-equivariant theory, whether it be cohomology or K-theory or something else, is the possibility of localizing at fixed points and not losing information. And so the idea is that if you have the inclusion map of the fixed locus, then you get a restriction map on K-theory of vector bundles. Because that's contravariant, like cohomology. And you get a push forward map on K-theory of coherent sheaves, because that's covariant and for proper maps, and this is such a proper map. And we can say even more when X is non-singular, which is an assumption that I'll put into place shortly, but not quite yet. So what I'll call the localization package consists of three things. I'll emphasize that they're a little different. So first of all, something that you can say about conditions when these maps become injective or surjective, or maybe an isomorphism, usually after inverting something. So we're going to invert some characters in the ground ring. So all of these maps are maps over the representation ring. So when I say inverting something, I mean inverting something in the representation ring. So that's the first part of the package, and in some sense the most important part. The second part, which is what gets used the most maybe, is a formula for computing push forwards, and in particular the push forward to a point. Which is the representation ring, and this is this gets identified with the Euler characteristic. I'll show you Equivariant Euler characteristic. So this is the kind of thing that well, as I've written it in terms of vector bundles, this requires X to be non-singular and complete, but you can do this for singular compact varieties if you take coherent shapes instead. So this is something that's often called like an Atia dot type formula. Other names get attached to it. And then finally, a description of the image. Of the restriction map. Again, say in the non-singular case. Okay, and this is something that gets called either Chang-Shelburne theorem or Gresky-Cutlet's recursion. And the one thing I want to just point out is that these are at least in principle, distinct components of the package. So you can have a condition where you're able to describe the image, but the map is not injective, and so on. So like different hypotheses go into each part of this. Okay, I'm afraid though, there's one very important thing that I didn't get to cover, just in terms of the basics, last time, and to even begin to even talk about, for example, what sort of things you need to invert, which is obviously important. I need to talk about the self-intersection formula. So I could call this self-intersection, or how I learned to love stop worrying and love the coastal complex. So coastal complex and self-intersection. That's what I'll write though. Okay. So let's look at just a very simple example of an inclusion of the origin in a vector space, considered as an affine space. Okay. And the sheaf just the structure sheaf of that point as an equivariant module over affine space has a resolution by vector bundles. And it's well, there's other possibilities, but there's a famous one called the coastal complex, which I'll write down. So you start with a OV. This gives it the structure, and then you start extending this. And it's a basic fact that this is that this whole sequence is exact, so it's barely zero. So that's the coastal complex. And I'll give it for now, I'll just this is a little bit, I'm going to call it like a little capo, because I want to refer to it at least once later. And explicitly, let me just to make sure that this is completely clear to those of you that anyone who might not have seen it before. What's happening here is this, I'm just thinking as a polynomial ring, net variables. This is a direct sum of such things. One for each dual coordinate. So I'm choosing a basis of the dual. And the map just sends the dual coordinate e dual to xi, right? That's the map. And so, in fancier language, the statement is that the xi's form a regular sequence, and whenever that happens, you can canonically extend it to a complex like this that is exact away from where they all vanish. Okay. So, but the conclusion of this being exact is that in the K-theory of E, which by homotopy is the same thing as the K-theory of a point, which I'm calling the representation ring, you have I can replace the class of this sheaf with the class of this complex. That just means I write it as an alternating sum. So O of V is 1, and this is V dual plus wedge 2, V dual, and so on. Okay, so if I write that in one line, that's I equals 0 to n minus 4 to the I, like I equal. Okay, and this particular formation associated to a vector space or a vector bundle is called lambda minus 1. So this is a definition. So this shows up all over the place, and you should think of this as like the Euler class. So in cohomology, you have an Euler class, the top Turing class of a vector bundle, and this is the analog of that. It shows up in the places where the Euler class would show up in cohomology. I think I can try one more thing here to make this still more explicit. So suppose T acts on V by characters, just like we did at the end of last time. U1, UN, and this says that I get a formula for the structure sheet in this K ring, and it's like this. Okay. So maybe it's a little exercise to convert this formula into that, but I hope you can believe that when you see the alternative signs, just the expansion of that. Okay, so this is a pretty, this is a nice formula, and it's going to show up a bunch. All right. Say a little more about that. The coastal quantities. So this coastal complex, nice and script. So it's exact away from zero, and this this gets you a restriction homomorphism. So this kind of goes the opposite way from what is what I generally promised yesterday. So this is K-theory of coherent sheaves, and this is a restriction. It's not by a flat map, right? The inclusion of a point, a closed point, not a flat map, but by resolving the structure sheaf here into vector bundles here, you then restrict the vector bundles. That's what we did. So let me just write some notation for this. So I got any sheaf here, I can send it to. So I'll use this notation as just kind of restricting the zero or to the point, really. And by definition, this is going to be minus 1 to the I. And what I'll do is take, I'll tensor F with the coastal complex and take cohomology. And because coastal complex is exact away from, it's an exact sequence of vector bundles away from zero, the cohomology will be supported on zero. So let's see, she's supported on zero. But you also might notice that what I've got there is a free resolution of this sheaf O of 0. And so what I've actually just computed, each one of these things computes the Tor sheaves between O of 0 and F. So this is just almost the definition of a computation of Tor sheaves. So that's sort of a canonical way of saying how they restrict. And sorry, that looks like a dual sign. Let me just write. Now I'll write V. Z, not a dual. All right. So that's how Tor sheaves should work. Okay, so in identifying So again, by homotopy, this is the homotopy property from before. Not by this map, right? So in there, I get a formula for the restriction as, well, it's lambda minus 1 of the dual times f. So, so inverting lambda minus 1, I can write a formula for f, and I'll want to come back to this. I want to write this down. I want to hit it in front of you at least once. Okay. So this is like the beyond Rossmann equivariant multiplicity that I think Bill talked about in his lectures. So this is like a K-theory version of the equivariant multiplicity of a point, or the sheaf at a point. And I'll make that more precise a little bit later. Okay. And I want to say one more thing about this because it's so concrete. So it lies in a localization of our sheaf. So it represents some T module. But possibly infinite dimensional. In this case, the case I'll talk about definitely infinite dimension. So let me just write it out. So example of that. So let's just take f to be O of v, and I'm going to regard that as polynomial ring. I'm using notation a little bit. So in that case, well, this is this restriction is just one because I'm looking at just the vector space, the fiber in that case, and we get this formula. So the class of this is equal to 1 divided by 1 minus. So, right, this one here is an example of lambda minus 1, the dual in that case, right? So, because that's 1 plus e to the minus u1 plus and so forth. E to the minus un. That's the plus higher degree terms. And this is exactly the multigraded covariant series. So another word for K-theory equivariant multiplicity is multigraded covariant series. And in that sense, Rossmann would actually, they go back before the corresponding notion in cohomology. Okay, so let me write down the self-intersection formula. So this is the 0 point, the origin of a vector space is the local case of the 0 section of a vector bundle. Okay, and so without belaboring the details, I'm just going to write down the analog of all this for the global case. So this localizes to the self-intersection formula. And so here's the proposition, whose proof I won't give except to indicate that the local case I did just describe. So we've got an inclusion of a regularly embedded closed subvariety. So regularly embedded means it has a normal bundle of the codimension. And in other words, and then there's some, locally at least, there's some coastal complex. We have the self-intersection formulas are always about take a class in here, push it forward, and pull it back. And nope, this isn't a surprise because I told you to expect this to play the role of the top trend class. And this is in Equivariant K-theory of Z. So we're this is and I guess I didn't tell you, I didn't exactly tell you how this pullback is constructed. The pullback is constructed either like this, if you like. So that's the self-intersection. So far. Okay. So now we can talk about localization. So now, okay, so this is this sort of corresponds to the first item, which is what I'm calling the main case. So we're going to assume X is non-singular and mostly for kind of pedagogical convenience, finite fixed limits. So here's the theorem. So at each fixed point, I have a cotangent space and it has some T action because it's a fixed point. And so, locally each one of those looks something like this. So this is something that lives in the representation. And let's take any multiplicative set containing this element that I've chosen. Okay, so that's not a then I'm going to give a condition for this. I invert characters and push forward. I may use the just regular push forward notation. and the restriction. These things are isomorphisms. If the rank as an RT module is equal to the number of fixed points. Okay, this is a completely spurious hypothesis that makes the proof work, and it is just true without it for other reasons. Like this rank is always held, but I'm not going to prove it. So let me just so let's do the proof. So this can be proved in cohomology, and the proof here is exactly the same as in cohomology. And so what you do is you look at the following sequence of maps, not exact sequence, just a composition of maps, the homomorphisms. So the Equivariant K-theory of the fixed look, this is just a sum of copies of the representation ring. And because X is non-singular, I can identify coherent sheaves with vector bundles, and then I can pull back to the fixed locus. And it's another bunch of copies of the representation ring. And the point is that the composition of this map, this is, I'll just call it, I pull back and I push forward. So this is diagonal. Right, if P and Q aren't the same, then this is like intersecting P and Q, and so we get 0 by a property we mentioned last time. And it's multiplication by n-1 of dpx on the P factor, or summand, I guess, by self-intersection. So this element that I denoted C up there is just the determinant of the map. Invert it and you get an isomorphism. And so that means that after inverting, this becomes surjective, but the rank condition therefore means that it must be an isomorphism too. And this one also has to be an isomorphism. So that's the proof. I mean, localization.
Maybe a silly question. Why is the equality dimension?
Which one? This one? Oh, this one. Yeah. This is X is non-singular.
Okay.
So this is what I call the point per isomorphism.
Okay.
So so that was the sort of first part of the localization pattern. The second part is this sometimes called the Equivariant integration formula, or generally just a push forward formula. And in fact, it's a pretty quick corollary of this theorem. So let me write it down as a corollary. And let's assume also that X is complete so that I can talk about push forward to a point. Um, so the push forward in K-theory. So I'm not gonna kind of elide the difference and using the non-singular X. I'll elide the difference in K-theory coherent sheaves and vector bundles. So this is equivariant for the characteristic. I guess I shouldn't be putting this in statement of the theorem, sorry. Parentheses. Yeah, but I'll continue doing it. It's a class, sends it to alternating sum of HI. Okay, so then the statement is you can compute this as a sum over fixed points, where you just look at how the torus acts on the fiber at each fixed point. This is just some T representation. And you divide out by standard denominator. The sort of like the Euler class. Okay, but this is an equality that takes place in RT. So this is a sum of rational functions. And it's equal to a Laurent polynomial. And I think, as Bill also mentioned in his lectures, this provides you with a whole bunch of error checking. If you made a mistake in computing one of these characters or one of these, it will show up almost certainly in the fact that when you try to sum up, you don't get a Laurent polynomial. So it's a strong condition to give you some error checking. So that's, and yeah, I think this is sort of obviously very useful, but I'll also try to convince you that some examples shortly. Yeah, let me sketch the proof. So the sketch. Gonna be an idea is here. So we're going to use so the point is that we have I need to say for alpha. So here's the claim. And it goes back to, oh, unfortunately, something I erased, but it's still indicated over there. Sorry, times the classical point. So the left-hand side is something that lives in here. And the right-hand side, maybe lives in either one of these, choose it. And so the main claim is that this is true. And again, by this, to see why, you can assume that alpha is the push forward of something that came from beta. So it came from the fixed locus. I guess I have to invert. Right, and if alpha came from here, from there, then this is just self-intersection. In that case. Right, just by clearing the denominator. That's the word. Oh, yeah, I guess if I need to say something about okay, I said it was a sketch. Then you should say something about how push forward to a point is just summing up over the fixed locus. Sending each one of these guys goes to 1. All right, so let's do an example. This is sort of a famous example that I think in the lectures on Equivariant K-theory, it's probably obligatory to do this again. So I don't know how, I think in this audience, it's safe to know that pretty much everyone knows what I mean by G mod B. I'm not going to just refer to Bill's lectures from a month ago, but probably several in between. But you can also think of GLN mod upper triangulars, just the flatter. Fine. And so there's the torus. I guess I should need to say this. It's the torus. Maximal torus in P, so diagonal matrices. And for that maximal torus, the fixed points of the torus action by left multiplication are naturally, well, maybe, yeah. There's an identification of them with the Weyl group. So I think of this as symmetric. And so I want to look at so there's finitely many fixed points. I want to look at the tangent weights to G mod B at each fixed point. I'll say what they are. So at the identity point, well, the nice thing about Lie groups is that they have the algebras and it's cooked up to be the Lie algebra to the tangent weights kind of are almost by definition the roots of G that are not the roots of B. So that's the negative roots. So I'll write roots as beta. Okay. So this means that going to -1, oh yeah, let me just say. And the way that the action of the Weyl group on roots goes, it's also cooked up to be intertwining with the action of the Weyl group on the fixed points itself. So this also says that the weights of T acting on the fixed point W are the W transits of the negative roots. So this means that I can write T dual, so I can write this this denominator that I'm going to need to compute if I want to apply a formula like this as just the product over beta and the negative roots of 1 minus, okay, and I dualize, so I get negative beta. And so there's going to be some negative negatives that are going to cancel out the launches. Okay, so we're looking at the flag variety, and we just found a formula for the sort of the K-theory Euler characteristic at each fixed point. Okay, so for I just realized there's a lambda and a lambda minus 1. Maybe I'll try to keep this lambda curly. So this is now a weight of an operator. So we get a line bundle L lambda, and it is defined to be. Let me get into my conventions here. So I believe Bill talked about these two. These are my conventions now. So W naught is the, maybe I should mention W naught. W is the longest element. And you can think of W naught as the one that just reverses order if you think about permutation. So that's what it does. It's the longest element. So when I write this, I just mean the one-dimensional representation where T acts with that character. Okay, so you have it's a fun little exercise in just the definition of this balanced product to figure out what the weights are. Maybe do you guys remember what this is? Maybe I should recall what this thing is. So this is the set of pairs G and V modulo the relation that I multiply on the right on G. That's the same as multiplying the left on V. And the way I multiply the left is by taking this character and scaling. So that's what this line bundle is. And then it's a line bundle just by projection on the first vector. Okay. So a little exercise in kind of playing through what this relation does tells you that the restriction of this line bundle to that fixed point is just this character. That's a characteristic permuted. Okay. So that's good. So here I've computed the denominator in this Atiyah bot push forward formula. And here I've computed the numerator for a particular line bundle. Okay. And so this, so applying the corollary, I get a formula for the Euler characteristic. Line bundle. So it's a sum over fixed points, where the fixed points are the violet group. And in the numerator, I'm supposed to put this character. And in the denominator, I'm supposed to put lambda minus 1, but we computed what lambda minus 1 is. So this is over W of. So there's a nice formula. And so I'll leave a little bit of algebraic sort of. Those of you who want some exercise in the Lie theory, or simple Lie theory, this gets you to the following formula. Yep. So I got a minus 1 to the length of W, that's the number of inversions. E W lambda plus rho, all divided by a common denominator, which is the product over all. Now I'm doing positive roots. Right. Beta over 2 minus B. And this is what's known as the Weil character formula. So in order to make a little sense of that, I'll think I can bracket it over here. When lambda is anti-dominant, meaning that, so if it was a partition, it's written in increasing order. Then, oh, hold on. Yeah. Okay, I guess I should put a question mark because I'm a little momentarily confused about whether I want the anti-dominant or dominant. So in that case, it's either dominant or anti-dominant. The higher cohomology of L lambda vanishes. And so this gives, so the Euler characteristic then, which is alternating sum of cohomology groups, is actually just the 0th cohomology group. But furthermore, this is equal to, yeah, I wanted dominant, sorry. The way I set things up, I wanted dominant. So lambda itself is a partition, if you're thinking it's combinatorially. So this is isomorphic to the irreducible representation, the highest weight lambda.
Oh, cool.
Oh, do you think it's a dual?
Okay.
Yeah, I think you're right, actually, because there's a W not involved.
So Dave, what is rho in your function?
Yeah, thanks. Rho is the 1/2 of the sum of all positive roots.
Sorry, could you explain how to interpret the denominator and the top sum?
This one?
Yeah.
Geometrically or, yeah, so
Sorry,
in the context of the story I'm telling,
no, just like what is the product over and
oh, the product is over, the product is over W. I'm sorry. Thank you for, yeah.
you're already summing over W.
Hold on. Oh my gosh. Thank you. Yeah, lambda should not be in the denominator.
Okay.
But maybe there's no
No,
W
this-
not there.
W, this is a W. This is right.
But maybe there's no W not in that exponent of the denominator then. Because you're not shifting a line, those are just the tangent space waves, so. And that e to the W naught beta, maybe that W naught shouldn't be there, but
This one,
yeah, because you're not shifting, those are just the weights of the tangent space of W.
you're right, and I subtly fixed it
Oh, you,
because by putting an R plus there.
oh.
Do you like me to get rid of that? I'll get rid of that. Yeah,
That was a little too subtle.
yeah, I'm sorry. You're absolutely right.
No, I just.
You know, it was too subtle for me as Stephen pointed out. Needed some translation between my notes and the Blackboard. Okay, let's get it right. So what was it? W of beta. And this is over beta. Okay, so now I think this looks exactly like it's supposed to, right? Oh no. Minus. Okay, I think it's okay now. I better leave it like. So this is just meant to be lambda minus 1. Right, so if I've gotten it right, this should be just a translation via Tiabat formula. That's what's meant to be there. Okay. Let me see. So the second part of my talk is going to be perhaps a little bit longer, but now is a good stopping place to take like a 5-minute break. So maybe let's do that.
Molesto, pero después ya cuando hizo efecto.
No Wi-Fi.
Let's discuss something.
Maybe there's another power outage just coming that we don't know.
Already.
De hecho, lo estamos viendo.
20 minutes is fine.
Él se excita mucho. De hecho, a mí la mejor. Es literal lo más grande que no. La gana la.
Okay. All right, so I gave you something like a very easy proof of this very basic case and often useful case. Yeah, you can get the valid character formula out of it. But let me tell you the facts a little bit more generally. So let's invert all characters. Well, 1 minus e to the u for all characters. So the theorem is this. We invert all these characters. And this is what I push forward. Okay, there are no further hypotheses on X. So X is singular, not compact, any X. But you'll notice that I've only done this for coherent sheaves, and I don't know such a theorem in this generality for vector bundles. So something like this was proved by Thomason. She proved it for higher K-theory as well. And it has a longer history going back to, well, in some sense going back to Attia, but maybe Baum, Fulton, McPherson, Court. So I'm not going to give the proof of this, but I'll just kind of indicate just the roughest sketch of the proof. So the idea is you take the complement of the fixed locus, and we use the exact sequence that we looked at last time. And here's the push forward map. In order to get the result I want, so I want this to be an isomorphism after inverting something. In order to actually make that conclusion, I need to have something over here. And what goes over there is K1. So whatever that is. So it continues. What you need to do is, so the key point is to show that when you localize at something that has no fixed points, you get 0, right? So U is an instance of something that has no fixed points, so then you get 0. And okay, and I guess I need to do this for K for K0 and K1 at least. And it turns out to be true for all higher K3. Okay, so one can do this, and that's all I'm going to say about it.
So does X like reduce or?
It doesn't matter.
So X is like any finite type scheme.
So this statement on K0, for those who do not know K1 and higher, it's kind of hard.
I don't know a proof without K1. So one thing about higher K theories, K1 is easier than K2. K1 is something that you can write down, at least in some cases. So there's at least a hope that you could do this without Quillen's construction, but at some point you just bite the bullet and learn Quillen's construction. But it certainly does make reading the papers about this a little difficult. Yeah, so with that out of the way, I get to skip a page of my notes. We're not going to do the rest of this proof. And we get to just use this. Yeah, I guess I could say, like, showing this statement for K0 is not that hard. You can follow a pattern that's kind of well developed. Do it the affine case and glue together. But that doesn't get you all the way. Okay, so let me say a little bit more about equivariant multiplicities. So I'm going to put in quotes, recall, pretending that everybody was here for Bill's lectures, but I'll write a statement. So say in Chow groups, I guess I have to invert something. So you may need some hypothesis, like all the let's make the hypothesis such that all characters on the Zariski tangent space non-zero, you can write. We'll call it the Chow equivariant multiplicity of the point in X. And what you're doing, one way to do it is to take the fundamental class of X, restrict it to a point. I'll say what I mean by that in a second. And then take the product of the characters. I'll just do it this way. U1, UI. So these are the characters of the tangent space. And what do I mean by the numerator? Well, you use one way to say what I mean is to take the tangent cone at the fixed point, and that's by the kind of the Foltman-Pearson degeneration of the normal cone, what I mean by restricting X to P. Okay, so this is a class in the this lives in some localization of the equivariant cohomology of the point, well, or of the tangent space, which is isomorphic by a Polytope. The equivariant cohomology. Okay. And when I talked about equivariant multiplicities in K-theory before, this is what I was thinking of. This is like an Euler class of the tangent space, and yeah. There's another way to characterize these, and that's what I write down. So we'll define K-theory equivariant multiplicities. So we use at the end, we're going to use this main localization theorem. And I guess I should have written it the other way. If the natural map goes this way, but I want to write OX as a sum of something times the classes of a point, and I'll just call that something the equivariant multiplicity. So let's continue to assume xt is finite. This can be done without assuming that, but in applications this will be done. So this defines some element. This right here is a direct sum of S inverse. So I'll call that the K-theory equivariant multiplicity. Okay, we already saw that if P is a non-singular point, then this equivariant multiplicity has a simple description for the U's of the characters of T acting with tangents. So it's 1 over this Euler. And I didn't say it, but I didn't say it in this generality, but I almost indicated it. If X is affine, well, an affine variety with a torus action is the same thing as a ring with an M grading, a grading by the character group. It's now I need more room. So another way to compute this equivariant multiplicity is it's just the multigraded Hilbert series. Okay. Now, there's some hypothesis needed in order to make this. We need to assume, for example, that these are all finite dimensional. There's some hypotheses that will guarantee that. So this is one manifestation of equivariant Hilbert series. So just remind me of that. So how do you compute these things? Well, one way is, I guess, suppose you could try to just ask Macaulay 2 to compute your Hilbert series for you. But here's another way. And this is, I think, the first place where condition of rational singularities. So take a desingularization. So let's assume X has rational singularities and take a desingularization. And again, this is just not strictly necessary hypothesis, but it'll make the statement cleaner. So I want to make sure that the inverse image has finitely many fixed points. Okay, then the equivariant multiplicity that we're interested in is equal to the sum over all fixed points in the fibered of the equivariant multiplicities. There. And these ones we know by the non-singular case. So these ones are known. By the non-singular case. So that's one way to compute these equivariant multiplicities, assuming you know how to desingularize. So the proof of this is again using the main localization theorem. So this map just sums up, I mean, it sends. Yeah, so if I look inside here, the part that corresponds to T, that's inverse this. That's sorry, to P. And over here, I've got all the things in the fiber. So this map here is just summing up all the contributions. And so that's where the sum is coming up. And this map, well, the key point is that because we have rational singularities, push forward of the structure sheaf goes to the structure sheaf, and that's where rational singularities come. So what that means is that push forward of the structure sheaf is equal to the structure sheaf. In other words, X is normal. And all the higher direct images of the structure sheaf are 0. So these taken together, along with the definition, means that the K-theory push forward makes structure sheaf to structure sheaf. Okay, so then you just kind of follow that diagram around and you get the. What's let's take X to be the affine toric variety. Associated to a cone. Okay, and I'm using the notation from Fulton's book, so N is the dual lattice of the character lattice. The lattice of one parameter subgroups. We associate toric varieties to cones in N, and explicitly, what you do is you take some semigroup algebra corresponding to the dual cone. The lattice points to the dual cone. Okay, so now I really am going to kind of assume that people have seen this stuff, and I'll give some examples in a moment. Okay, so such a toric variety. Yeah, let's make it a pointed cone. Pointed and full dimensional. Pointed full dimensional cone. In that case, there's a unique fixed point. And it has, well, in this case, you can just look at the graded Hilbert series in a way, anyway. It has, I'm just going to keep track of the characters in here. And break them. So what I'm going to do now for the next 10 minutes or so is work out a bunch of examples that lead up to saying something, using Equivariant K-theory to say something about lattice points in polytopes. So let's look at a very explicit example. Let's take this cone. Okay, what's my lattice? My lattice is going to be blue. Okay. Here's the cone. So it's generated by, again, I'll use the standard base of T1 and T2. So the generators are 2 T1 minus T2, T2. Sorry, these I should give these. I didn't want to give these names. That's all these duals. Because the thing I really want to generate is the dual cone. So the dual cone is easy to see in the two-dimensional case. It's the dual cone is generated. This is what I want to call T1 and T2. So it's generated by T1 and T1 plus 2 T2. So this toric variety is not smooth. It's a singular quadric. And you see that by the generators of this semigroup here. There being a relation, the sum of these two is equal to twice this one. But I can, if you like, you can just kind of try to enumerate the lattice points here, and I'm going to do it in a dumb way that I'm sure you can improve on while you watch me write. So there's the character 0. There's T1. There's T1 plus T2. There's T1 plus 2 T2. And you can go on and list these out forever. So easy exercise, find a better way to do that in 30 seconds. But let me, I'm trying to make a point here, so let me make that point. So instead of doing things directly like that, let's resolve and you can resolve singularities of a toric variety by subdividing the cone, by subdividing the fan. In this case, it's just a straight cone. So I'm going to subdivide it like so. And here I've got something that I'll call sigma 1, and here I've got something I call sigma 2. So this toric variety is essentially the blow up of the first one. And let's look at the two cones. Okay, so that one's pretty easy. Here's the lattice. And the other one. So this is generated by T1 and T2, and this one is generated by T1 plus 2 T2 and minus T2. Okay, so these are both smooth cones. And because these are smooth, so each one of those patches is smooth, it satisfies the hypothesis of this theorem. Toric varieties have rational singularities. I can apply the theorem. And I know what the equivariant multiplicities are, so I'll call this P1 sigma 1. Maybe I'll just abbreviate P is sigma 1. Well, that's 1 over 1 minus e to the minus t1 is t2. Oh, I'm sorry, this should be just plus the way I've set it up. But these are already dual characters. And for sigma 2, it's sigma 2. The same kind of thing. So 1 over 1 minus e minus t2. T1 plus T2, 2T2 times 1 minus e to the minus T2. Okay. So apply the theorem, and the theorem says that that graded Hilbert series I was trying to compute is equal to the sum of these two. So I'll write them out one more time. And maybe I won't write them out one more time. So it's the sum of these two rational functions, this one and this one. And you can either try to work that out in by hand, or you can do both. You can also ask computer algebra to jump it for you, or you can have done the exercise and done it the easy way in this case. But here's what you get. And the fact that this is not of the form 1 over some product of characters is a manifestation of the fact that this is the standard. For any x, I still want to work with toric varieties, but let me just remark that for any x with finite fixed locus, I can compute the Euler characteristic of a vector bundle by taking its different multiplicities and summing up like that. So this uses I guess complete x. Then I can talk about this push for it. That's basically so. So we're gonna do that. Gonna use this. Okay, so let's do things about lattice points. So we have a lattice polytope with vertices ui. I'm gonna let sigma I, maybe I should have called it the dual, but we'll call it sigma I now. This is going to be the inward tangent cone. To be at the vertex. So what I mean is if I got something like polytope like this, and here's my vertex. So here's P. then I just look at all the vectors that point into the polytope. So that's the Simonyi. And I guess I should say I want this to be translated to the origin. When I talk about sigma I, it's like the natural cone, so that's the translated. So then so what's left? So the P, or chi P, the generating function for lattice points in the point. Okay, so the theorem, which can be stated, and so far I'm stating it mostly without any reference to K-theory, is that this generating function for lattice points is a sum over vertices of these equivariant multiplicities associated to these cones. I guess I should have called this attention. And shifted by US. Oh, shoot. Yeah, I'll go over here. Yeah, so for example, okay, so here's a polytope that everyone in this room loves. Oh, no, has been growing to love as we've seen it. Matroid's all here. Okay. So here is the two-dimensional permutohedron. I can write down its generating function. There's 7 lattice points here. What's it there? Okay, and Brion's theorem says that this 7-term polynomial is a sum of 6 rational functions. Okay, so that may not impress you much, especially when you see the rational functions. So, okay, there they are. You just take one for each tangent cone, 5, 6, and I mean, you can translate these into x's and y's for T1 and T2. Maybe it's a little surprising that you just get polynomial out of it, but it's true. So
Do you shift the numerators?
yeah, thank you. I was trying to do this quickly. Thank you. So the first one is 5. E to the T1. E to the 2T1 plus T2. Thank you. It's not going to be true if I don't shift the numerators. Okay, so now it looks even more wild. Okay, so the statement is that chi p is equal to the sum. So that may not impress you much, except that if you think that the same thing is true, if I take an enormous dilation of that same. I'm not gonna bother, but let's say there's multiply that polytope by 1,000. Then there's going to be some enormous Laurent polynomial, and it'll be a sum of the same 6 rational functions where the only thing I've done is modified the numerator. So I NP equals the same sum with modified numerators. And as far as I know, this is actually what's used in integer programming. It's one of the most efficient ways of computing the number of lattice points in a polytope. All right. Okay, so that's those are the 2 main applications I wanted to discuss. Oh, yeah. The proof is apply the localization formula to the toric variety versus
So can you do it when P is not very ample? No, like normality.
No, there's no normality issue. Yeah, so it basically, one reason is this. So you do it on the singular toric variety itself. The only input required is the equivariant multiplicities of each point.
But which singular toric variety? The one associated to the fan of P or the one really given as image of the monomials that correspond to points of P?
Well, okay, the normalization of the latter, I suppose.
Which is given by the.
So I'm just counting points in P, I'm not doing Ehrhart theory here.
Okay, I think I see.
Does that make sense? So another thing you could do is just resolve, so subdivide your fan, resolve, and compute the not very ample line bundle on that. And it's the same. And rational singularities is doing a lot of work here. Okay, let's see. Am I gonna make it to Riemann-Roch? Maybe. Okay, so at this point, I have a choice. I can either do Riemann-Roch, or I can talk about the image of the restriction map. And anyone who wants to hear about the thing I don't talk about can stay afterwards. Can I do a poll? How many want to hear about Riemann-Roch? Oh, no. Okay. How many want to hear about the image of the restriction map? All right, Riemann-Roch wins. I'll talk to you guys afterwards. Okay. Let's do, well. When you take a plebiscite, this is what you get. All right. Oh. So let's talk about your name. So in topology, equivariant Riemann-Roch theorems predate equivariant algebraic K-theory. They go back to the 60s, almost to the very beginning of K-theory. So this is a T.N. Siegel in the 60s. And what you quickly realize that you need some algebraic completion. Will be required. And you realize this already in the case of a point. So let me say something about it. So equivariant turn character is going to be a map from K-theory to some completion of Chow groups, and the nice, well, I don't know if it's nice, but the fact about this is because this is just a graded ring. You can write this completion as just the product of the child groups. So rather than a direct sum, it's a product. Sums of infinitely many non-zero components. Okay, so that's what it is. It's a ring homomorphism. And as a ring homomorphism, it can be characterized by the property that it sends the class of a line bundle to the exponentiation of the first term class of that line bundle. So it's say 1 plus the first term class plus 1/2 of the first term class squared. Okay, so without T,
So you're using two coefficients.
yeah, thank you. You have to complete and tensor with Q. Okay, so without T, the sum is finite. Because eventually you run out of degree. But with the T, it's essentially always infinite. So let's see. So let me get a statement. With T, basically, usually. Okay, so completing whatever this means by completing here, it's just that. It means something where I allow infinite sums. I need to say something more canonical about what I can what I'm meant to do on this side in order to get something like a Riemann-Roch isomorphism of the type that's familiar from the finite dimensional case. So thank you. Is in the representation ring of T, take the augmentation ideal. So that is to say that it's generated by all, well, it's generated by all the things I inverted when I wanted the localization theorem. So this is just for all characters. And another way of saying that is it's the kernel of the equivariant K-theory of a point to the non-equivariant K-theory of a point. This is R of T. Okay, and so we're going to complete KT of X with respect to the I-added topology. So when I write down completions, that's what I mean. Okay, so here's the theorem. So as I'm stating it, so some version of it goes back to T and Siegel. But the algebraic part is edited now. So after completing and answering with rationals, Turing character factors through through an isomorphism. Write it down. So whenever I complete on K-theory, I'm doing it with respect to the augmentation ideal. The train character is what I. So this is a functorial, yeah, it's a functorial. Functorial isomorphism. And then also, in this one, there's no, I don't know anyway, the topological counterpart. So this is, the second statement is fairly editing grant. You've got the same kind of thing on K-theory equivalent achieves. And so you have to, so now this is a module, but you can still complete it. Then you can complete the Chow homology groups. And this, I'm gonna, for the purposes of the next 10 minutes, I'm gonna call this the homology Chern character, but it's often denoted tau, and I think it goes back to Baum-Holden McPherson, the non-constraint setting. Okay, so both of these are functorial.
What is the map?
Yeah, what is tau? So defining it is not so easy. It's not so hard. So the way you need to define it, so this is the Baum-Holden McPherson construction. You define it for smooth things. In fact, first you define it for a projective space. And then it's the Chern character. And then one way to do it is to use the technique of equivariant envelopes to reduce to the projective case. And yeah, so it's not, I guess the short way to say this is it's not very explicitly defined by characterizing properties.
Does it involve the top class?
It's related to the type class,
But
but
like,
it doesn't have to be constructed, I think, directly in terms of.
But like when you say it's functorial, like the Todd class should.
Okay, yes, so, yeah. Yes. So the dot class has to show up. Yeah. So the corollary of functoriality is not as anticipated. Is that, let's look at this diagram. So here's my, this is the sort of the tau isomorphism. And because I'm going to denote S bar, just because this lives in, so I guess I should write this. So S is an RT, the kind of characters that I like to invert. The S bar lives in the equivariant homology of a point. And one way to think of it is these are going to be all 1 minus U, and these ones are going to be just all. And I guess I should, so in tensor of Q, I think by inverting S, that's okay. So the localization theorem says that I get a localization isomorphism at fixed points. So let's assume it's do finite again. Just for simplicity. Well, there's an analogous localization theorem that I think Bill talked about on Chow groups, which says that when you invert characters, you can fix points. Let's follow what happens to so functoriality says that this diagram commutes. So let's follow what happens to.
You're assuming X is not singular here, just so you're gonna have these restricted maps. Is that weird?
No, I guess the natural map goes this way. Sorry. X is definitely potentially singular. But the nicer results will be when it's non-singular. Okay, so let's follow what happens to the structure sheaf. Well, one thing it does do, and I think this is answering Matt's question, is it goes to the homology Todd class. So that's over here. So one needs to define this. I've reduced the definition of this to the definition of this, so that maybe not tell you anything. On the other hand, this goes over here to by the definition of equivariant multiplicities to the equivariant multiplicities, the sum over. And well, there's equivariant multiplicities in Chow groups too. And so those will be the Chow equivariant multiplicities of X and the Chow class of the fixed point. And okay, the structure sheet of the fixed point maps to the fixed point itself. There's nothing going on there. This is just what the points. This is sort of your idempotent each side. And that means that you get this nice relation. Todd class. So locally, the Todd class is yeah, and here I wanted to call this map. I do want to call this map churn. So this is just a copy of. The bottom row is just the usual churn character because everything is non-singular. Just fixed points. So this says that the churn character of the equivariant multiplicity, the K-theory equivariant multiplicity, is equal to the Todd class restricted to point times the Chow multiplicity. Or in other words, the Todd class of X restricted to a point is a ratio of equivariant multiplicities. And this is something very familiar in the smooth case. So if P is non-singular, then the Chow equivariant multiplicity, so I guess I should say that the characters on the tangent space are U1 through Ui, and the Chow equivariant multiplicity is 1 over the product of the characters. We've already seen the K-theory multiplicity. Churn character of e to the x is e to the x considered as a series. And so this says that in the smooth case, the Todd class at a fixed point is the product over the tangent weights of well, I take the ratio of these. So when you saw Bernoulli numbers and stuff coming up from that, this is one way that it's get. Okay, so the next thing I wanted to say was a geometric picture of localization in Riemann-Roch, but that required me to talk about the image of the restriction map. So I think what I'll do is stop here, and I still have enough voice left for the 2 or 3 of you that wanted to hear about the image of the restriction map. I can hang out and talk to you. But thanks for listening.
Questions?
So for example, so I didn't know this origin of Brown's theorem, but like, I had this origin, but for example, if there is this application of Brown's theorem to the Birkhoff polytope that is very interesting, but intractable, but so is it good to go back to the geometry to do the decomposition and study it, or just kind of apply or like apply it?
So the most honest answer is I don't know. I spent like, I don't know, a little time with Barbanok's book a couple years ago. And my understanding is that if you want better algorithms for computing lattice points and polytopes, Brion's theorem is a starting point, and it's still like sort of the seed, but then you do sort of bespoke tweaks to the algorithm, and that's really on the combinatorial side. And it's not clear to me that further analysis of the geometry of the toric variety of the Birkhoff polytope will help. One can hope, but I haven't seen.
It looks like Todd discovered his classes long before Chern discovered his classes. How is this possible? You know, it looks like the natural order of things
Is Chern and Todd.
yeah.
Well, I mean, you could even say the natural order of things is equivariant cohomology of a point. And then, but yeah, I have no idea how he discovered.
If there are no more questions, let's thank Dave.